Hi everyone, welcome back to my channel Narada Life Academy. It's been a long time I haven't been posted any videos regarding hydraulics, and today we are going to discuss about the loss of air due to sudden enlargement of the pipeline, and this is from this I've taken this from minor air loss chapter. Okay, here you can see there is an abrupt change in diameter from smaller diameter to larger diameter pipeline here, and when water flows, the water will not be able to follow the boundary. Here the boundary is like this, and the water cannot follow the boundary of the pipeline. So there is some eddies will be formed, and there is a separation of the flow. Here you can see this is the flow is separated. So here the eddies are formed, and this type of eddies are seen here, and this is why the minor loss occurs due to this transition. And minor loss is also called point loss. It's not like a main loss which is given by the DeCH2.1 equation. So this is the point loss. Minor loss is occurring. You can see at this point there is a sudden enlargement. So we have to derive this today, the derivation, and to do the derivation, we apply the physical laws, and the physical law you are using is here there is a change in momentum, so you are applying the momentum principle, and also the continuity obviously, and then the Bernoulli. Okay, so you are applying the Bernoulli from this point 1 to point 2, and you are using the continuity equation, and because in hydraulics we use these principle in many derivation. So without any delay, let's enter into the derivation. So let's define the variable here. Okay, so here the variable you can see here, the P1 is the intensity of pressure, at section 1, and likewise P2 is the intensity of pressure at section 2, and you can see this acts as between this just before and just after section of this point loss. We can assume this as a control volume, and always the pressure forces acts towards the control volume. So you are showing this right here. This is P1 A1, and this is P2 A2. Okay, because we are not writing the pressure, we are writing the pressure forces, because we are going to apply the Newton's. We are applying the momentum principle, so that's why we need to have the forces. So that's why I'm writing here the force toward the control volume, and these are the pressure forces. And P1 and P2, the intensity of pressure acts at section 1 and section 2. And we are not addressing the weight of this fluid, inside this one, this section, because it acts in the vertical direction. We are going to apply the physical law in the horizontal direction, so that's why I'm not showing it right here. And there is a velocity V1 here, because it is a smaller diameter. A smaller diameter has the higher velocity, and this is a larger diameter, it will have the lower velocity. So there is a change in momentum. Okay, so P1 and P2 are this, and A1. What is A1? A1 is a cross-sectional area. Cross-sectional area at 1, and A2 is the cross-sectional area at 2. And V1 and V2 are the V1 is the average velocity at section 1. And V2 is the average velocity at section 2. Okay, because there is a change in velocity due to the change in diameter. I've already mentioned you. I've already told you that there is the water cannot follow the boundary. So that's why the flow is going to be separated. So it does not follow the boundary. The flow separates, and the eddies are formed, and due to this phenomena, there is a minor loss that is called sudden loss due to certain enlargement of the pipeline. Okay, so now let's write the let's apply the Bernoulli. Apply the Bernoulli between section 1 and 2. Okay, so if you apply the Bernoulli between 1 and 2, let's apply this one because this is very close to each other. So the elevation can be neglected here. Okay, so let's apply the Bernoulli. P1 by gamma plus P1 square by 2z plus Z1 is equal to P2 by gamma plus P2 square by 2z plus Z2 plus, there is no length loss, there is no Darcy-Weisbach back friction loss because this is very close. So that's why we are only dealing with the sorting enlargement. So that's why I'm only taking the enlargement loss, that is HE. So I'm writing this as an enlargement loss. So that's why I'm writing this HE. So let's cancel this out, Z1 and Z2, because why? It's section 1 and section 2. There is no elevation change, so that's why I can cross it down. So I can get P1 by gamma minus P2 by gamma, and minus plus V1 square by 2z minus V2 square by 2z is equal to HG. Okay, so this most value is loss due to sorting enlargement. So that's why I can say this is the equation number 1. Okay, so this is okay. Now let's apply the momentum principle here. To apply the momentum principle, so we need to find out the net force acting on the net force acting on the control volume. Okay, so net force is summation force is equal to this P1A1 in the right side, so plus P1A1. And this P2A2 in the left side minus P2A2, and there is another force due to eddies. Okay, so another force due to eddies, that is this cross-sectional area is A1 and this cross-sectional area is A2. So this eddies, due to this eddies, there is another force, that is P dash, that is in the direction of motion of the fluid, that is P dash into the area is how much? The area is this eddy area. Okay, so eddy area is A2 minus A1. So that's why you are going to write here A2 minus A1. The pressure, intensity of pressure due to eddies act along the direction of flow experimentally, and the area is A2 minus A1, and then you are going to get this eddy area. So that's why you are going to write plus P dash A2 minus A1. Okay, so this is how you write. And let's find the summation force is equal to, let's separate this, P1A1 minus P2A2 plus P dash is experimental, that is P1A2 minus P1A1. Okay, because P dash is experimentally, P dash is equal to P1. So that's why I am writing P1A2 minus P1A1. The P1A1 is already gone, and there is a net force you are going to get is P1 minus P2 and multiply by A2. You can say this is our equation number 2. Okay, I have applied I have calculated the net force, and the net force is going to be P1 minus P2 into A2. Why I am doing this? Because I'm going to apply the momentum principle after this. Okay, so to apply the momentum principle, I need to find out the rate of momentum here, and I need to find out the rate of momentum here, and I am going to subtract this, and I am going to get the rate of change of momentum. So when you get the rate of change of momentum, and you can equate it to the net force, and that is called momentum principle. Okay, so we are applying the momentum principle. For that, we are going to find the individual momentum rate at different section. So let's go to find out the momentum rate. Momentum rate at section 1. Okay, momentum rate at section 1. The momentum means what? Momentum means rate of change of momentum, mass into velocity by time. Momentum rate means mass into velocity by time. At section 1, mass into velocity by time. Mass and the density. Mass is density into volume. Mass is density into volume into velocity by time. So volume by time is discharge. Density into discharge into velocity. And from the continuity, discharge is area into velocity. Okay? So I have got the expression for momentum rate at different section. So momentum rate is how much now? The momentum rate is density, momentum rate, that is density into discharge is how much? Area into velocity into another velocity, that is velocity square. Okay, this is how you write. And let's write the notation of these momentum rate at 1. Momentum rate at section 1, that is rho a1 v1 square. And now likewise you can say momentum rate at section 2. What is momentum rate at section 2? Momentum rate at section 2, that is you can directly write this as rho a2 v2 square. Okay, the same process you can do, and you can directly write this rho a2 v2. Now my purpose is to find the change of momentum, that is the rate of change of momentum. What is rate of change of momentum? Equation number 4 minus equation number 3. That is, so I am going to subtract this, that is rho a2 v2 square minus rho a1 v1 square. I am going to do this rho a2 v2 square minus rho a1 v1 square. Okay. So now I have got expression of rate of change of momentum, and I am going to equate this to the force, net force. Okay, that is a momentum principle. Okay. So now what I am going to use the continuity equation right here. Continuity equation, that is a1 b1 is equal to a2 b2. Okay, and you can say that. So use this one here. Let's separate this a1 is equal to a2 b2 by b1. Okay. So let's substitute this a1 above there and make this a2. Okay. So I'm going to substitute this above here. So I'm going to substitute this above here to get the expression in terms of a2. So let's substitute this above, that is rate of change of momentum. When you do this, we are going to get rho a2 v2 square minus rho a1 is how much? a1 is a2 v2 by v1, into v1 square. You are going to cut this v1 and v1. You are going to get how much? Rho a2 v2 square minus rho a2 v1 v2. Okay, you are going to get this rho a2 v2 square minus rho a2 v1 v2, and I am going to take the common here, rho a2 common, that is v2 square minus v1, rho a2 v2 square minus v1 v2 is going to be the expression. Rho a2 common, that is v2 square minus v1 v2 is the expression. I am going to do this equation number 5. Okay, this is a rate of change of momentum. This is the rate of change of momentum, that is going to be rho a2 v2 square minus v1 v2. Okay, so let's apply the momentum principle, that is net force is equal to rate of change of momentum. Okay, so that is net force is equal to rate of change of momentum. How much is the net force? Already I have got the net force is, that is P1 minus P2 into A2. So net force. Okay, so how much is net force? Net force is P1 minus P2 into A2, and this is going to be rate of change of momentum is how much? Rho A2 V2 square minus V1 V2. Okay, I have got this one. So I'm going to get P1 by gamma minus P2 by gamma from here, and I'm going to substitute this in equation number 1 to get our answer. Okay. So let's go to make it P1 by gamma minus P2 by gamma. Let's go to make this. This is now you can plot this A2 and A2. You can plot this. Okay. And let's divide by gamma here. P1 minus P2 divided by gamma in both sides. That is rho divided by gamma V2 square minus V1 square. Okay. And gamma is rho, P1 by gamma minus P2 by gamma. I got P1 by gamma minus P2 by gamma. That is rho divided by gamma is rho g. So that is going to be V2 square minus V1 V2, sorry, V1 V2 square minus V1 V2. And you can cancel this rho and rho, and you are going to get P1 by gamma minus P2 by gamma, that is V2 square by G minus V1 V2 by G. Okay, and you can say this is equation number 6. Let's substitute this P1 by gamma minus P2 by gamma in equation number 1. Equation number 1 is what? P1 by gamma minus P2 by gamma, plus V1 square by 2G minus V2 square by 2G is equal to LC. Okay. So let's substitute this P1 by gamma minus P2 by gamma over here to get the value of LC in terms of velocity. Because we know the velocity from the discharge divided by area, you are going to get the velocity, and by putting just the velocity, you are going to get the sudden sudden enlargement. Okay. So now let's substitute this above here. I'm going to erase this one. I've got less space here, so that's I'm doing this. So please follow me, and let's put this over here. What do we get? That is V2 square by G minus V1 V2 by G. That is plus V1 square by 2G and minus V2 square by 2G is equal to LC. Okay. So this is how you write, and I'm going to take the LCM here. LCM is how much? That is 2G. 2G is LCM. Let's take 2G is LCM. 2G LCM. What do we get? That is 2 V2 square minus 2 V1 V2 plus V1 square minus V2 square. Okay, this is how we write. And LC is equal to V2 square minus V2 square minus 2 V1 V2 plus V1 square. V2 square minus 2 V1 V2 plus V1 square by 2G. Here you have got this V2 square minus 2 V1 V2 plus V1 square by 2G, and that is going to be LC is equal to, you can write like V1 square minus 2 V1 V2 plus V2 square divided by 2G. So if you do this, what do we get? This is the expression for V1 minus V2 whole square divided by 2G. Okay. So this is how you got the sudden loss due to sudden enlargement, and I'm going to write it here. V1 minus V2 whole square divided by 2G. 2G is not in the bracket. Okay, it's outside the bracket. So V1 minus V2 whole square by 2G. This is the outcome of the our derivation, and you are going to do this derivation. This is important. Can be asked in final exam. So this is the important derivation because we have used the continuity concept here, and we have used the momentum principle here. Okay, and we have also used the Bernoulli principle. So that's why all the physical laws are used in this derivation. So I recommend you to watch this video, and give me the feedback also. And okay, see you in the next video. Thank you for watching.